Welcome to this explainer. Today we're essentially running a high-tech system diagnostic on the US tax architecture. I mean, think of the economy as this massive, intricate operating system. We want to see exactly how it operates, where the inefficiencies are hiding, and how policymakers attempt to balance the sheer efficiency of the machine with the human need for fairness. Okay, let's dive into this. To really grasp the sheer scale of this whole system, we've got to look at the raw data intake. We're talking about federal revenue collected back in 2014, which clocked in at a staggering $3.3 trillion, right? It's a number so huge it's almost hard to process. So let's bring it down to earth a bit. If you divide that massive data stream by the US population at the time, it breaks down to about $10,235 per average taxpayer in the economy. That is the baseline load this system is pulling from its users every single year. So here's our diagnostic menu for today. We'll start with the system specs, then look at system friction, move on to a rate analysis, check out the fairness protocols, and finally, uncover the ultimate trade-off. All right, part 1, system specs, US taxation. Let's look at where these massive streams of government revenue actually come from. You'll notice right away just how top-heavy the federal government's revenue collection really is. The absolute largest streams, personal income taxes and payroll taxes. You've probably noticed taxes deducted from your paycheck, right? Well, one of those is FICA, which is a payroll tax on the wages firms pay their workers. This specific stream is absolutely vital because it funds massive social subroutines like Social Security and Medicare. Combined, personal income and payroll taxes make up the vast majority of the federal system's fuel. Meanwhile, down at the state and local networks, they collect about a third of all taxes in the economy. But here's the thing, they run on an entirely different kind of fuel. To keep their localized servers humming, state and local governments rely heavily on sales taxes, which are levied on your everyday retail purchases, and property taxes, which are tied to real estate. Now, they do also receive massive data transfers directly from the federal government to help manage shared programs, but their core native code, it's really built on what you buy and what you own. Moving on to part 2. System friction, tax efficiency. So now that we know where the resources come through, we need to talk about friction. Because let's face it, no digital system is perfectly smooth. Every single time the government extracts revenue, it introduces friction into the economy, which economists measure as tax efficiency. The absolute biggest bug in any tax system is something called dead weight loss. And this isn't money that goes to the government, it is pure economic value that just vanishes into thin air. Why does that happen? Well, it's because one of the most fundamental principles of economics is that people respond to incentives. When taxes alter those incentives, human users change their behavior. They consume less, they produce less, and the whole market shrinks. That lost value, that's your dead weight loss. Let's run a quick practical simulation to see how this builds up. Imagine 2 users, Jake and Jane, and they're buying pizza. The price of a pizza reflects the cost of making it, which is $5. Jake values the pizza at $8, so he gets a $3 surplus value. Jane values it at $6, getting a $1 surplus. Everyone's happy, right? But then the system architect adds a $2 tax, pushing the price up to $7. Jake still buys it because his $8 value is higher than $7. The government gets its $2. But Jane? Her value is only $6. At $7, she just cancels her order. Here's the crucial point. The government gets 0 revenue from Jane, but Jane loses her entire $1 of surplus. That lost mutually beneficial interaction, that is exactly what deadweight loss is. But wait, deadweight loss isn't the only friction in the system. The second big source of friction is the administrative burden. Just think about the sheer processing power, the time and the money that taxpayers burn through just trying to comply with an incredibly complex tax code. The resources spent hiring accountants, tracking down receipts, and optimizing for loopholes, none of that builds roads or funds schools. It's simply burned up in the friction of compliance. And that is a massive drag on overall system efficiency. Okay, part 3, rate analysis, average versus marginal. To understand exactly how this behavioral friction scales up, we have to look at the underlying math of the tax code. The key to understanding user behavior really comes down to the difference between 2 critical metrics. Your average tax rate measures the total fraction of your income that the government takes. It's a great metric to gauge your overall sacrifice. But your marginal tax rate, that's what the government takes from your next dollar of income. And if you add up all federal and state labor taxes, the marginal rate for a typical worker is sitting at about 40%. Why does this matter? Because rational people think at the margin. If you're deciding whether to work 1 extra hour, your marginal rate dictates exactly how much you're penalized for that extra effort. It's ultimately the marginal rate that creates that deadweight loss we talked about.
So this brings up a really fascinating query for our system diagnostic. If marginal rates cause all this friction, behavioral change, and deadweight loss, what is the most perfectly efficient, frictionless tax code we could possibly write? How do we build a system with absolutely zero bugs?
Well, the mathematical answer is astonishingly simple: a lump sum tax. Imagine the government simply charges a flat $4,000 to every single person in the network, regardless of their income, choices, or actions. Because the fee is completely static, your marginal tax rate is zero. Working harder doesn't trigger a tax penalty, buying that pizza doesn't trigger a tax penalty, you don't need any accountants, which means zero administrative burden and zero deadweight loss. On paper, it is a perfectly efficient system. Which brings us to part 4, fairness protocols, tax equity. But, as you might have guessed, there's a huge reason we don't actually see lump sum taxes in the real world. They fail almost instantly upon deployment because they violate a core piece of human programming, our profound desire for fairness, or what economists call tax equity. So how do we program fairness? There are 2 main philosophical algorithms we can use. First is the benefits principle. This acts kind of like a toll road. You just pay for what you use. If you use the public parks or the roads more, you pay more. The second is the ability to pay principle. This dictates that users should make an equal sacrifice based on their actual wealth. Because, let's be real, a $1,000 tax might be a minor inconvenience to a billionaire, but it could be a devastating loss to someone living in poverty. Now, if we select that ability to pay principle, it breaks down into 2 distinct subroutines. First, we have vertical equity, which basically means that richer taxpayers should pay more. Then we have horizontal equity, which means that taxpayers with the exact same ability to pay should contribute the exact same amount. Sounds simple enough, right? Well, let's see what happens when we actually try to translate this into law. Let's look at vertical equity first. Pretty much everyone agrees the rich should pay more. But the big question is, how much more? System architects can structure this in 3 ways. In a proportional tax, everyone pays the exact same percentage, let's say 25%, regardless of their income. In a regressive tax, high-income earners actually pay a smaller fraction of their income than low-income earners. And in a progressive tax, high-income taxpayers pay a much larger fraction of their income. The U.S. leans heavily into a progressive structure for income taxes, but deciding exactly how steep that progression should be, that is a constant, ongoing debate among policymakers. And horizontal equity is honestly just as glitchy. Look at this classic dilemma. The Smiths and the Joneses both have a gross income of $100,000. Under strict horizontal equity, they should pay the exact same tax. But what if the Smiths have massive, unavoidable medical bills, while the Joneses are perfectly healthy but have huge college tuition bills for their kids? Do they truly have the same ability to pay just because their gross incomes match? Should the system give the Smiths a break for being sick, or give the Joneses a break for educating their kids? This exact dilemma is exactly why our tax code is thousands of pages long, completely filled with special provisions and deductions. Furthermore, any attempt to program real fairness has to account for tax incidence, and this is a massive variable. Because taxes alter supply, demand, and prices across the board, the user who ultimately bears the true financial burden of a tax might not even be the one the government originally billed. For example, if you tax a corporation, they might just raise their prices, meaning the consumer is actually the one paying the tax. You simply cannot program true equity without understanding exactly where the burden actually lands. And finally, part 5, the ultimate trade-offs, equity versus efficiency. We've analyzed the inputs, the friction, and the fairness protocols, which brings us to the final output of our diagnostic run. The fundamental reality of designing a tax system is that architects must manage a constant, unforgiving trade-off. Optimizing for perfect efficiency, like with our $4,000 lump sum tax, completely destroys equity and fairness. But on the flip side, layering in complex equity protocols, like deductions for medical bills, progressive tax brackets, and special exemptions, well, that creates massive administrative lag and high marginal rates that cause all that deadweight loss. You literally cannot maximize both at the same time. The economics of this diagnostic run can tell us exactly how the machine works. It shows us exactly where the deadweight losses are, how user behavior shifts, and who bears the ultimate burden. But the ultimate question isn't mathematical. It's a question of our shared values. If you were the system architect, tasked with writing the code for millions of citizens, where would you set the sliders between fairness and efficiency? It really is the ultimate design challenge. Thanks so much for joining me for this explainer, and I'll catch you next time.